Hey everybody, today we're going to talk about simple DC circuits. DC stands for direct current, as opposed to AC, which is alternating current. Basically in DC circuits, the current continuously goes in the same direction. In AC, it alternates. In this class, we're going to focus a lot more on DC. Now, to form a circuit, basically to get the electrons to flow in the first place, you need a few ingredients. Those ingredients include a power supply. This will be a source of potential difference. Don't forget as well that potential difference is just another word for voltage, and voltage is the amount of potential energy per unit of charge going through this circuit. You're going to need a closed loop. Without that, there's no way to connect one voltage to another. You're going to have some conducting material. Usually this is the form of some sort of metal wires, and you're going to have a source of resistance. Now resistance is provided by a resistor, and it's measured in ohms. And the main purpose of the resistance is just to slow the flow of current. So the higher the resistance, the less current you're going to get. Without a source of resistance, you'd get infinite current in a circuit. That's really bad. The battery power supply provides the voltage, which is also known as potential difference, which is also known as electric potential, and that's measured in volts. As an electron goes through the circuit, it picks up voltage in the battery, and then it drops it off at each individual resistor. The current is the amount of charge per second passing through a section of wire. So the units of current are just a coulomb per second. It's also known as, you can kind of think of current as just the flow of electrons, the flow of these charged particles. With water, for example, you can measure current in a variety of different ways. A lot of people choose speed, but that's not exactly the best way to do it, because if I've got a really small stream going at 2 miles per hour, or a really big river going at 2 miles per hour, there's a lot more current in that big river than the small stream. So probably a better way to do it is to line up at one spot on the river and pick that point and then count how many water molecules pass by in any given second. This is kind of similar because each electron carries the same amount of charge. So this is just counting the amount of charge in coulombs passing by in any given second. And that's going to be an amp of current, 1 ampere of current. Right. Oh, and current is also denoted by the letter I. So speaking of water, here's a picture of a really pretty waterfall. I've mentioned before in class how very similar electricity and gravity are. So here's another example about how this can work using water instead of electrons flowing through essentially a circuit. Pretend that over on the far end here, there's a pump that brings the water back up, and then it loops around, and then it goes over the waterfall. And this is just a continuous flow. So pretend the river doesn't start elsewhere and end up in the ocean ultimately. Instead, it's just a contained closed loop with a pump and with a waterfall. Now, the waterfall is, in this analogy, kind of like a resistor. The analogy breaks down because resistor slows the flow of current, waterfalls pick it up, so that's not perfect there. But it's a really good analogy in other ways. So as water goes over the waterfall, it loses some potential energy, some gravitational potential energy. You started at one height, you ended at another. That change in energy had better be the same change in energy that the pump provides, because I need to be back up to the same starting point before I can go over the waterfall again. I'm not going to go up any higher or go up lower. I'm going to go up the same height. So in one direction, it's losing energy, then the pump lets it gain energy. The pump is basically an analogy for the battery, and the waterfall is an analogy of the resistor. Here's what a similar circuit would look like. The symbol for a battery is typically a small line parallel to a big line. The big line is typically the positive terminal. The small line is typically the negative. And if you've got multiple cells lined up, then you may draw multiple. I kind of alternate between just one combination and several when I do it. But that's the battery symbol. The resistor symbol is this weird squiggly line. That's what adds the resistance to it. So when current leaves, oh, by the way, conventional current flows from the positive terminal of the battery to the negative terminal of the battery. Now, what kind of charges would do that? Well, positives are repelled by positives and attracted to negatives. So much like the electric field, conventional current is what a little positive charge carrier would do throughout this circuit. We have since realized it's electrons that are moving around, but we were too lazy to change our conventional current direction. So in this class, we're going to go with conventional currents, pretending like the charges that move around are positive. They're really negative. They're really going in the opposite direction. But it doesn't matter because all our numbers work out regardless. So when you leave the battery, you're at some high voltage. When you go over the resistor, you drop off your voltage just like that waterfall, and you're back down to 0 volts before going back into the negative terminal of the battery, where it acts like a pump and brings you back up to a high voltage, where you drop it off at the resistor again, and this continues over and over and over again. Now, waterfalls can get a bit more complicated than just one single drop and we're done. Some waterfalls have a series of steps. Now in this case, I'll drop some potential energy off at waterfall 1, I'll drop some potential energy off at waterfall 2. They're not necessarily going to be the same. In this picture, it looks like U2 is a little bit bigger than U1. But when the pump brings it back up, then the grand total, U1 plus U2, needs to add up to whatever energy the pump is adding to it. So I could find the energy that the pump is supplying to this water molecule just by simply adding the total of the drops, the total from the waterfalls. It's the same thing over here on circuits when you get a couple of resistors in a row. So as current leaves the battery, goes over resistor 1, it drops some of the voltage off, but not all the voltage from the battery. When it goes over resistor 2, it drops some of the voltage off, but not all the voltage from the battery. But when you add up V1 plus V2, it will equal the total voltage from the battery, so I'll be at 0 volts before going back into the negative terminal of the battery. Just like you're at 0 height before you go back into the pump, brings you back up to the top, you go over your little step waterfalls again. This is what's called a series circuit. A series circuit. By the way, if you haven't noticed from these waterfalls, all of the water that comes out of the pump goes over waterfall 1, and all of the water that comes out of the pump goes over waterfall 2. There's nowhere else for the water to go but through both resistors. It's the same thing here with our circuit. All of the current that comes out of the battery also goes through resistor 1 and it goes through resistor 2. Because there's literally nowhere else for these electrons to go, because there's no place where the circuit splits off and gives it a choice of paths. All the electrons that come out of the battery go through R1 and R2 in a series circuit. Now, the reason I bring that up is because sometimes current does split in nature with waterfalls as well. When this happens, the total energy that's dropped is the same whether I went over waterfall 1, waterfall 2, or waterfall 3. Oh, whoops, I wrote 2 twice there, didn't I? There we go, that's better. So, whatever path I go over, I'm starting at 1 height, I'm ending at essentially 0 height. And then I'm having the pump bring it back up, and that total change in energy provided by the pump is equal to the drop at 1, or it's equal to the drop at 2, or it's equal to the drop at 3. It's the same thing in what's called a parallel circuit, when I have multiple different paths I can choose, but each path only sends me through one resistor. In that case, I gain voltage from the battery, the pump lifts me up, and then, if I'm an electron, I start leaving the terminal of the battery, I come to this first junction point, and I can either go to the right, or I can go down. But I can't do both. As a single electron, some of my other electron friends will make the other decision. So the current splits, just like with the waterfall. Some of the water goes over waterfall 1, some of the water goes over waterfall 2, but the same single molecule is not going over both. So the current splits, and but no matter which path you go down, you're still dropping the same total voltage, because when I get to the bottom, I better be at 0 volts before I go back into the battery. So in this case, my total voltage equals voltage 1 equals the voltage over R2. In the series circuit, our total voltage is added because it was a series of steps. Now, I'm still traveling over just one big waterfall and I'm done with it in this sort of a circuit. So the total voltage is the same in parallel. What's different is with the series circuit, all the current that left the battery went through both resistors. That's not the case here. Some of the current chooses path 1, some of the current chooses path 2. So here I'll have I total leaving the positive terminal of the battery until I get to the junction point where I'll call I1 the current that goes through R1. I'll call I2 the current that goes through R2. By the way, there's a junction point down here. So I1 arrives at this junction point, I2 arrives at this junction point, and then they both travel together back to the battery. So I'm back to I total when I get back to the battery. So when it comes to current with parallel, it simply adds to the total when you bring all the paths back together. So that's the main difference between series and parallel. Now, of course, you'll also end up with some waterfalls where one path you take, you have a series of steps within that path. Another path, you're dropping all off at once. Sometimes it can become a huge mess where you have some parts of it that are in series together, and you have some parts of it that are in parallel. So here's my series, here's some parallel branches. So we're going to work on how to break these circuits down because it gets a little more complicated. But we'll do that in class later. Now, throughout all of this, the guiding equation, the one guiding equation, is V equals IR, just saying that voltage equals current times resistance. Now, this can be applied to the entire circuit. So if you zoom in on the battery, all of the voltage that's being supplied by that battery equals the total current that it's pumping out times the total resistance of this circuit. It can also be applied to a single resistor. So if I zoom in on one of my little waterfalls, then the total voltage dropped at that resistor equals the current going through that resistor times its own resistance. Or you can apply it to a simplified group of resistors, which we'll do later in class as well. Another rule that you need to know is Kirchhoff's voltage rule. This is pretty simple. Over the course of one path, the voltage gained equals the voltage dropped. I already kind of talked about that with the pumps and the waterfalls. And if a circuit has multiple path options, each path results in the same voltage drop. Now, sometimes you'll have multiple resistors on a certain path, so in that case, the total of that group of resistors will equal the total voltage drop of the paths in general. But we'll get there later. You've also got the current rule, which is the total current coming into a junction equals the total current going out of the junction, always. So again, I've already described series versus parallel, but here's a nice little chart that kind of breaks it down. So the current is the same in series resistors, but the voltage drops add to the total. Versus parallel, the voltage drop is the same across each resistor in parallel. The current adds to the total. From this, and we'll go over the derivation in class later, you can find the equivalent resistance. I mentioned earlier the grand total resistance of the circuit equals the total current coming out of the battery. The grand voltage of the battery equals the total resistance of the circuit times the total current. V equals IR. So for a series circuit, to find the total resistance, called the equivalent resistance, it's just the simple sum of all your resistors in series, those steps. For a parallel circuit, where they're all lined up, and you're going over each waterfall, just one waterfall per path, then it's this weird reciprocal rule. 1 over the total resistance equals 1 over R1, plus 1 over R2, plus 1 over R3, and so on and so forth. Now for the energy of a circuit, we talked about way back when we did voltage, that it's simply the change in potential energy divided by a test charge, where voltage is defined as energy divided by Q, joules per coulomb. So therefore, if power is the change in energy over time, and we know that the change in energy is a charge times voltage, that means power is charge times voltage over time. And if I separate this out, I can get charge over time times voltage. And this gets me to our main takeaway, which is what you actually need to write down, that power equals current times voltage. P equals IV. All right, so I think I've thrown enough at you for one video. So take it easy. Bye.